I have been working with an excellent group of colleagues to understand why it is that some geomagnetic storms with particularly strong solar wind and ionosphere coupling produce lower than expected thermospheric density upheaval. This work, sponsored by Air Force Research Lab, AFOSR, and NSF, is actually coming from the operational community. Space Command has noticed that there are some events for which their forecasts that are based on ground-based indices simply do not represent what happens in terms of upheaval of thermospheric density. So that's the motivation. It is ops to research rather than research to ops. The outline is I'll give for the students a little bit of background on neutral density and explain what some of these unexpected responses are in these in some of these storms, but not all of the storms. It appears that there's a solar cycle dependence. I'll give you a tale of system science, what we know, what we suspect, and a whole list of unknowns, and then try and tell you a little bit more about the last words in the title, Sheath-Enhanced, and some words that aren't in the title, solar cycle dependence. So for the students in the audience, when the atmosphere is heated by either particle deposition or dissipation of Poynting fluxes, Joule heating, and some other processes, the atmospheric molecules and atoms fight for more room. When they do that, at a given level, in their motion, a new motion, they would attempt to go down, but the atmosphere is exponentially increasing in density as you go down. There's not enough room for them. Even as they try and move sideways, there's not a lot of additional room. But they can find additional space if they move up. So when the atmosphere is heated, the atmosphere heaves up. And this nice example from 2004, 10 days starting on day 2003, ending in day 2010, is essentially a nice illustration of that. The blue part of this trace, which comes from the CHAMP neutral density, extrapolated, actually measured above 400, just below 400 kilometers, but referenced to 400 kilometers, shows us that the dayside density is at a fixed altitude higher, the nightside density is lower. So the dayside atmosphere is heated by the sun, it expands more than the cooler nightside density. What we have used as a community for more than 30 years to try and model this, and in particular to try and explain the effects of coronal mass ejections that increase geomagnetic activity and therefore increase heating, is we have worked with basically the AP index, which you notice here has a nice correlation with both the day side and the night side, but there are some significant gaps. In this case, the AP goes flat, and somehow or another, after this huge storm, the density in short order manages to go down to lower than it was before the series of storms started. And the question is, how can that happen? Well, we've known since the late 1980s that there was a chemical involved in this. It's a chemical called nitric oxide, which is an amazing molecule that cools the atmosphere in infrared wavelengths at 5.3 microns. I'll say more about that in just a second. Because Space Command realized that this AP index, which is just an accumulation of ground magnetic perturbations with a background removed, wasn't quite doing the job, and was also failing to provide kind of this long extension of, what happens to the density after the energy input stops. They adopted a modification called the Dst Index. Now this you might recognize as a magnetospheric index that measures the ring current. And you think, what does the ring current have to do with neutral density? Well, it has an amazing correspondence in that it's measuring enhancements of convection and current in the magnetosphere, and that does, in a rough way, relate to the energy coming into the neutral atmosphere. There's also an aspect of happenstance. It just happens that the time constant for recovery of the ring current is pretty close to the time constant for the recovery of this cooling of the atmosphere by all of the methods that the atmosphere has come up with. So these two are in combination now in operations at Space Command. So here's the deal. Here's a typical profile of a storm measured by the Dst Index. If there's a sudden storm commencement, sometimes we'll get that index to heave up or rise as the magnetosphere is compressed. And then we essentially see the reduction in the magnetic field at the Earth that is generated by the ring current. The correspondence, and I'll put minus 75 nanotesla here because that is the place at which Space Command declares that there is a storm of strong enough, of enough strength that they're actually going to switch to this Dst Index. What happens is with some time delay, we get an upheaval in the neutral density profile in a global sense. And the amount is several nanograms per meter cubed at 400 kilometers. So you might think, and this is what Space Command thought, that if this index goes more negative, this rise in neutral density in a global sense should be higher. So let's take a look at a group of storms that Space Command gave me. The blue are the problem storms, indicating didn't behave quite as expected. And the red are the control storms, equal numbers of storms, that are those storms interspersed that essentially were well forecast. You notice that the problem storms have two things. They have that very strong pulse at the beginning, and they tend to be stronger. So what do we expect with a stronger storm? We expect more neutral density upheaval. There's the expectation, and there's what we actually get when we do a superposed epoch analysis, which is a statistical means of lining up on a key time when DST hits minus 75, and essentially putting all of our storms together so that we can tease out the signal and sort of de-emphasize the noise. And I'll show you what the noise looks like here in just a minute. But the problem storms rise rapidly, and then they flatten out. They're just sort of underperformers in terms of neutral density. How can that happen? Here they are again. Now I've put the neutral density, and I thought, well, perhaps it's just a problem with the AP index. But if I, with the Dst index. But if I look at the AP index, those storms are bigger. There's no doubt about it. What's going on? Fortunately, we gained access to the timed SABRE data, which has been acquired now over the course of a solar cycle. And what we see in these unusual storms is copious amounts of nitric oxide emission. More nitric oxide is being created in these storms, and the question is, why? Well, why is nitric oxide important? It is essentially, as I said, a very strong infrared cooler. It has a thermostat effect. You put energy in, energy glows back out. It is controlled by electron precipitation into the auroral zone in the 1 to 10 keV region, and also by the temperature of the atmosphere. The higher the temperature, the more active the molecule is. So before the storm, after the storm. Now this has been known for a while, and Mariangela Fedrizzi and the whole group over at Ceres have been working on, estimating how much energy is coming in via particles, how much energy is coming in via Joule heating, and then what is the NO cooling rate that goes with that. So this is known in the community that these kinds of things happen, but what is not known, or was not known, is why we would get these unusual events where nitric oxide just took over. So here's a more of a spatial view of this, going from 0 to 90 degrees, and I took the liberty of flipping the southern hemisphere into the northern hemisphere so I could get some signal. Here is the 0 epoch time. Here's the nitric oxide flux in the problem storms before, and after, control storms before and after, you'll notice there's a little more nitric oxide even before these storms start. And I was curious, why is that? It turns out that these problem storms, if we look at the indices and remove an appropriate background, look at the indices coming from the corona, F10.7, from the chromosphere, Y10.7, Lyman alpha plus X-ray, every one of those indices is way up compared to the control storms. This means that the sun is, in fact, on the total disk, much brighter. It is capable, there's more energetic regions on the sun, they are capable of ejecting coronal mass ejections with greater speed, we believe. But that's a jump. We haven't proven that yet. What we have been able to show is using the DMSP data that the Poynting flux is about the same in terms of energy deposited between the two types of storms. But if we go interrogate the particles, the auroral particles that I mentioned, in the problem storms around the time of real storm onset, those particles are way up in terms of flux. Tremendous amounts of particle energy coming in, able to create that nitric oxide. Why is that? What makes them different? I just want to show you here problem and control storms. Here are the precipitating ions. And from the DMSP, you can see in the problem storms, there's a lot more precipitating ions. Why? We think it has to do with preconditioning. These storms in the solar wind have unusually high density. They have a very strong pressure pulse ahead of them. They have strong IMF, although the IMF-BZ is not particularly different. They have lots of ULF waves with them. So this, what Rich mentioned in terms of waves, those are there. There's something different in the structuring of the solar wind. There is something different in structuring in terms of the asymmetry of the ring current, and interestingly enough, in terms of the AU index, which we don't hear very much about, but it's the eastward electrojet, where if we have particles precipitating into the evening region and changing the conductivity, we will have an enhancement in the auroral electrojet. So what does this have to do with sheath-driven storms? Zhenpeng Guo et al. Did a series of papers comparing what it is that drives geomagnetic storms, and he looked at not just the CME itself, but the CMEs that are fast and actually drive changes in the interplanetary magnetic field ahead of them. They're called sheath-enhanced or sheath-driven storms. They have the characteristics that I just described in terms of high density, in terms of high dynamic pressure. So we are making kind of a leap of faith, and we've also been able to verify by just looking at the data that most of these storms are sheath-enhanced with northward IMF. Why northward IMF? It has something to do with the preconditioning. Here's what we think it is, but this is where we're just now beginning to engage the modelers, with much thanks to Benjin Zhang from Dartmouth. He gave me these images to show what happens when you have BZ neutral or BZ positive at the beginning of a storm. You form a cold, dense plasma sheet, a fat magnetosphere. When you then hit it with fast IMF BZ negative, there's tremendous tail stretching, a huge, probably at least in the first event, substorm, a huge plasmoid that goes down tail, and an incredible snapback dipolarization, forming a dipolarization front that drives particles, the cold particles, in very close to Earth, where they can interact with the plasmasphere and perhaps precipitate. That's my story now. I'll stick to it until some modeler gives me a better one. So we get enhanced particle precipitation, which feeds back to the nitric oxide. Okay, coming up on the end of this tail, is there a solar cycle dependence to this? We think so, because Space Command has been using this method of forecasting since 2001. And only in late 2004 and 2005 did the problem show up. That made me crazy. How could that be? It turns out that when we go from an odd to an even solar cycle, which we just did, 2004 to present, the magnetic clouds tend to have a preferred northward orientation coming in first. So there is a preferred orientation to the magnetic clouds. They're coming in primarily north field first during these most recent years, and if they happen to have a sheath that is also predominantly north field, then it is the perfect setup to fatten up the magnetosphere, stretch it out, let it go. And we feel the response in an operational sense for those folks who are trying to figure out what is the thermosphere doing. Is it heaving up or is it collapsing? And apparently,